Hi everyone, welcome to math class today on May 18th on this rainy Monday. Got a pretty good lesson for you here today. You just have to kind of sit back and pay attention. I got a lot of visuals, so hopefully you can see how this works. But basically I'm going to introduce you guys to what's called the Pythagorean Theorem today. There's no extra problems to try today. We'll start really problems tomorrow. This is more kind of showing and proving to you this concept, and it's one of those things in geometry. It's kind of cool how it all fits together. So I'm going to try to show you that here today. Now, what we're going to learn about the Pythagorean theorem, that it's based on the geometry of a right triangle. So we have to talk a little bit about a right triangle just to make sure we're all on the same page of what it really means to be a right triangle. So a right triangle, in case you forgot, a triangle, obviously three sides, but a right triangle has one of those sides, okay, that is 90 degrees, and you have that little right angle symbol there to show you that that's 90 degrees, okay. Now, these sides are pretty important the way that they're set up, okay. The two sides that make up the right angle, okay, the two that make the 90 degrees here, those are each called what they call the legs of a right triangle, okay. Probably because we have two legs and there's two sides that always make up the right angle. There's one other side that does not make up the right angle, that's across from it, and that one has a funny word called the hypotenuse. Okay? You just have to be able to recognize that word. It's not a word you have to know really well. It's a funny word. I always think of hippopotamus when you see it. But don't get thrown off by the language here. It's just that's the weird one, okay? This word Pythagorean theorem, it's just named after this old guy from like Greek times called Pythagoras, and that's why it has this weird name. He just named it after himself. So don't get thrown by that either. Now, to start off with this, and this is going to come into play later, what we're going to do, it's really important. Okay, they decided to come up with variables to start to deal with this, to try to come up with the thing that eventually became the Pythagorean theorem I'm going to show you today. So they tried to make it easy. They picked A, B, and C. A and B are the legs, and just to make it easier for today, it doesn't have to be, we'll make the shorter leg A and the longer leg B. And then C, the hypotenuse, okay? This is important. The hypotenuse will always have to be C, okay? It's always the longest side. It's always the side directly across from the right angle. And one of the ways you can kind of remember it is sometimes I look at it as this right angle kind of looks like an arrow pointing at the weird side C, the hypotenuse. Okay, but I'm going to use this idea of a right triangle today to try to show you kind of what the Pythagorean theorem is and one of the ways they can kind of look at it. Okay, so I'll come back to some of these notes here in just a second. So you can see I have kind of an interesting drawing here, and I'm going to have to zoom out just a little bit so you can see all the sides. Alright, bear with me just a second here. Alright, so it doesn't look like anything too creative, but this is all started off of, I made this triangle, alright, right here that you can see, that looks very similar to the one I just made. Okay? And I copied it 4 times. You can see I have A, B, and C the same way that I did for the triangle that we just made. So now I can go ahead and say, okay, alright, I can kind of line these up. I'm just rotating them as I do. And I'm able to make this square that I had already outlined on the outside here. I know it's a square. How do I know it's a square? Well, there's 90 degrees in every single one of the corners. Okay, let's see if I can focus this a little bit better. Looks a little better maybe. There you go. So there's 90 degrees in each one of the corners. Okay, and a square has to be all the side lengths the same. Well, if you look at each side, it's going to be A plus B, because this is B plus A equals this side. B plus A equals that side. B plus A. B plus A. So they're all the same side length, and that's just from these 4 four triangles that are made that I already labeled A and B. These four orange triangles are the same. But you can probably also see that there's another square that's formed here, and it's the square that's in the middle. Okay, I kind of made this yellow so you can see that a little bit better here. Okay, so this area in the middle, this is a square too. Again, I got 90 degrees in each corner. Whoops. And, okay, each side is C because each side of this middle square is the side C of my triangle, the hypotenuse. They're all labeled right there. So what we can say to make this just a little bit easier to think about, okay, is let's say the area of the big square on the outside, we don't know what it is right now, but when we don't know an area, or we don't know a value in math, we can just call it x. Okay, so the area of the big square is x. We'll just call it that for now. Now, if I want to say, okay, what's the area when I take away, what's left of the area when I take away, area left when I take away the four triangles? Okay, well, it would be x, and I take away my four triangles, and you can see that the area that's left when I take away four triangles here is just this yellow part, which is c squared. So x minus the four triangles leaves me with c squared here. That's the only part in yellow. Okay, now we're getting a little bit somewhere. Now, what's cool about this is I can reorganize these triangles now by just going ahead and kind of make a rectangle here. We're just going to kind of like tanagrams here. We're just going to try to make a couple of rectangles, see if we can fit these in here, because these are the same four triangles that we had before. Now, you can see here I have those four triangles that are in the middle of the big square, but now I have these two other side squares here, and it turns out these are indeed squares. They're all 90 degrees. This one, in fact, from, if you look at the side lengths of those triangles, that is A and this is A from my two triangles. So I can say this blue square, the area is A squared. And I look at the upper part, these are both B. Well, I know the area of a square is B times B. That is going to be the area of that blue one is B squared. Okay? So again, I have the same square. So the whole thing is X, but I can do the same thing. Remember the area left, you can't quite see it. Area left when I take away the four triangles was C squared before. Well, if I start with X and again I take away those four triangles, I could also say now the second time that the area left when I take away the four triangles, well, what's left now? Here's these two blue squares. It's also equal to A squared and B squared, A squared plus B squared. So the same square, if I take away the four triangles in the first diagram, I'm left with C squared. If I start with that same area of the big square and I take away those same four triangles, I'm also left with A squared and B squared. Well, what do you know about these two things right here? They must be equal. And you can see that from here. So again, I took away the four triangles here. Boom. When I took away the four triangles, I was left with these two blue squares, A squared and B squared. Or I can start with the first diagram, the big thing here, take away the four triangles, and all I'm left with is this yellow part, C squared. Therefore, A squared plus B squared has to equal C squared. All right. The last way I can show you this is just to kind of prove it to you on paper now. It turns out I measured all these squares, all right? Or I measured all these lengths, rather. Okay, it turns out that, just to prove it to you, this dimension A, okay, was 3 inches. The dimension of B was 4 inches, and the dimension of C was 5 inches. Okay, I picked these numbers on purpose because these ones make the Pythagorean theorem hold true. So what you can see here is that if I claimed that a squared plus b squared is the same as c squared, that's what we just said from right here on the paper, okay, that these two are the same. Well, we just said a was 3, we just said b was 4, and we just said c was 5. Okay, so 3 squared is 9, 4 squared is 16, 5 squared is 25, and sure enough, 25 equals 25. It works. But what was cool about the first way we did it is that we had a, b, and c there, which means those numbers could have stood for different variables, different numbers. This thing right here called a squared plus b squared equals c squared, okay, sometimes referred to as the leg squared plus the leg squared equals the hypotenuse squared, okay, that is what's referred to as the Pythagorean theorem. Okay, so this was just a little introduction to kind of show you how cool that it always goes together, and this holds true for all right triangles. And there's ways to work in reverse where you can ensure something is 90 degrees, because if the three values do work like this, then you know for sure, if you didn't know for sure that that was a right angle, but you know that a squared plus b squared equals c squared like it did here, well, that proves that this is a 90-degree angle then. And that's one of the things that's useful in building when you want to have 90-degree angles when you're building something. You want, your house that you're building to be square, the walls to be square, all those types of things. So it really is pretty useful. So we'll get into some examples with this tomorrow. I hope you enjoyed this little introduction video for today. And I also, I'll post another video or two along with it of some other applications. I found a football one this morning, so of course I got to post that one. All right, have a great Monday, guys, and tomorrow we'll get into some work and example problems of this. Have a great day. Bye.